Okay, so in chapter 5, we're going to learn about solution chemistry. And we're going to cover the concept first, which we kind of talked about a little bit towards the end of last week, where there's different ways of dissolving different types of solutions, let's say in water or really any solvent, whether it's a polar or non-polar solvent. And then we're going to talk about the net ionic equation, precipitation reactions, and things like that. So first, we need to talk about what an aqueous solution is. So an aqueous solution is anything that the medium or the solvent of the solution, meaning the main part of it, where everything is dissolved into, is water. So it's a water-soluble solution because the base, it's water-based. So if you ever hear of water-based, that basically means aqueous. And there's different types of solutions that could form from aqueous solutions. Could be salt water. There's a difference between salt water and sugar water. One of them is an electrolyte, the other one isn't. So we're going to learn about the different types of electrolytes. That's the first thing we're going to cover. Basically, that means different types of aqueous solutions. So salt water and sugar water, they behave differently. The way they're dissolved is different. And it all has to do with the way water is polar. And the reason why they dissolve at all is because of this phenomenon, that water is polar. Now, the water molecule, since we learned about ionic and covalent bonds, it's not ionic. We know it's covalent, right? Since they're both, the hydrogen and the oxygen are both non-metals, and they contribute to this covalent bond. But it's a special type of covalent bond, that being polar covalent bond. Now, the bond itself is polar, but more importantly, the molecule is polar. And that's because water has this bent shape to it. So later in the course, we're going to learn about electron and molecular geometries, meaning the spatial arrangement of different atoms in the molecules and the different spatial electron arrangements in the molecules. And these geometries have to do with or contribute to the polarity of the molecule itself. And what polarity means is there is an electron differential or a charge differential with respect to each atom. So in a covalent bond, we know that it forms from the sharing of electrons, sharing of valence electrons. But in polar covalent bonds, this sharing is not equal. So oxygen happens to be a lot more electronegative. And we'll learn about what that term means later, but basically, I'll tell you what it means. It means that in a covalent bond, oxygen likes to pull the electrons closer to itself a lot more than hydrogen does. So if it's a tug of war, imagine a tug of war, oxygen is a lot stronger than hydrogen. So it's going to pull the rope closer to itself. Now, what this does is it increases the electron density around oxygen, making it partially negative. It's not ionically negative. It's not that strong of a negative ion, but it's going to have this partial negative charge. And with that being the case, and the opposite of that, is hydrogen having this partial positive charge from the lack of electron density around its core. So that's what makes a polar molecule. Any molecule that has a net, what we call electronegativity difference, or a net asymmetry in electron density, we call polar. So the reason why water can dissolve different types of other polar molecules is because it itself is polar. There are things that are non-polar, which they cannot dissolve polar molecules, and they can only dissolve other non-polar molecules. So examples of that is really a lot of organic solvents are non-polar, and even the ones that are considered polar, they're weakly polar in comparison to water, like ethanol. Ethanol is pretty polar, but it's not as polar as water. But we can go over that another time. But so anyway, with aqueous solutions in water, there's two types of dissolution or dissolving. The first type we'll talk about happens when you have an ionic salt, such as NaCl. And NaCl, even though we know it as table salt, is not the only salt. There's many different salts. And what a salt is, by definition, is the ionic, or a soluble ionic compound is considered a salt. So any type, whether it be magnesium sulfate or sodium carbonate, those are all different salts. So in this case, in any of their cases, they have a positive and a negative ion. The positive ion is a cation, and the negative ion is an anion, which we know about. And the way they dissolve when they are entered into the medium, into the solvent of water, is the water molecules, because of their polarity, will have a charge attraction to each of the cation and anion of the ionic salt. So if you have sodium, which is in purple right here, okay, yep, which is in purple right there. So sodium is going to be attacked, and you see it's kind of surrounded by the red oxygen atom, right? And that makes perfect sense because we know from the last slide that oxygen is partially negative. It has this partial negativity to it based on the increase in electron density because of its polarity, or it's a higher electronegativity than hydrogen. So what will happen over time is if you put a salt crystal into water, even if you don't really excite the water at all by stirring it around makes it happen faster, but or changing the temperature or the pressure. But even if you just leave it there, what will happen is the negatively charged oxygens will kind of gang up and attack the positively charged sodium ions, and thus ripping them away from the rest of the salt crystal. So that's how dissolution happens for ionic salt, for soluble ionic salts. Some of you are thinking, oh, if you say soluble ionic salts, there must be insoluble ionic salts. And you're totally right, and we'll learn about those towards the middle of the class. Now, similarly, you have other water molecules in the solution, and those that will attack the negative anion. So you have the positive cations attacked by the oxygens of water, and the negative anion that's in green is attacked by the positive hydrogens because they're a positive negative interaction, and they will attack and they will solubilize the negative ions. So if you take this and over time, over the course of a couple of seconds, you have millions of water molecules attacking millions of, or less millions, of sodium chloride, thus ripping it apart into its ionic components. Now this gives the entire solution a charge because of its positive and negative ions. That charge gives it the ability to be conductive and to conduct electricity through it. So that's why we call this kind of solution, where you have the dissolution of ionic salts, an electrolytic solution or an electrolyte, because it has the ability to conduct electricity through it. So when you think of electrolyte, I'm sure you think about what drink? Gatorade, exactly, right. So what electrolytes mean in Gatorade doesn't mean if you drink it, you're going to get electrically, well, it does mean you're going to electrically charged, but you're not going to get zapped or anything. What that means is it's full of ions. That's literally it. And some of these ions are very important, essential ions for our muscles to move and to exert energy, such as magnesium, calcium especially. You have sodium, obviously, chlorine, a little bit, potassium, really a lot of the group 1A and 2As. And iron is in there too. Cobalt, not really. If you take multivitamins, you'll have some of the other ones like selenium, cobalt, copper, nickel. Those are ones that are trace elements that are in our body that are still important for our metabolic processes. Zinc, of course, zinc is very important. Okay, cool. So that's one type. That's where we have the electrolytic solution. Then we have another type of dissolution in water that is not electrolytic, which is called a non-electrolyte, but it still dissolves in water. An example of this is sugar. There are different types of sugars, but we'll just talk about generally, and they all behave the same in water. This is a sugar molecule. Now, sugars are an organic molecule, meaning they're based in carbon, and they have carbon, oxygen, and hydrogen, and they are polar. So they are polar just like water, but they can't be split apart into ionic components like sodium chloride can. So water is going to do what it knows best, and it's going to bond by an electrostatic interaction, and the positive charges of the hydrogen will bond to the partial negative charges of the sugar, while the partial negative charges of the water will bond to the partial positive charges of the sugar. So it'll kind of just make this polar interaction. But it won't rip apart the individual sugar molecules, but it will rip apart the sugar from its crystal. Let's say you put a cube of sugar into water and you stir it around a little bit. it's not going to be a cube anymore. It's going to be ripped apart into its molecular components, but not ionic components, because the sugar molecule, it has a ring. It's basically a ring with carbons and oxygens in it. It doesn't really split apart into its ionic components. So thus not being split into its ionic components, that means is it's not going to have a net charge at the end of the day. So no net charge in the solution means you're not going to have electrical conductivity. So that's the two types. Okay, so here is an example of how, let's say this salt, this is cobalt 2 nitrate, it's a salt, right? It dissolves into solution. Now, with cobalt 2 nitrate, CONO3 2, the way it dissolves is all of its ions break apart. So its cobalt becomes cobalt 2 plus by itself, and then you have 2 nitrate ions individually by themselves. This is important to know when we go over a complete ionic equation, is that the NO3 does not stay as NO3 when it breaks apart. It goes into 2 NO3 minus. Because each of the NO3s is connected to the cobalt originally, but when they break apart, each of the NO3s is now separate, and it's not connected to the cobalt anymore. So they are 3 individual ions that come off of one ionic salt. And some ions could have, or some salts could have, let's see, Na3. No, we have something more. We have up to 5 ions, I think, even more really. You could have, but yeah, the point is it's not always a 1 to 2 ratio like NaCl. So if you were to do concentration, or to figure out the concentration of cobalt nitrate, if you have 0.5 molar cobalt nitrate, it will have 0.5 molar of cobalt ions, and it'll have 1 molar of nitrate ions. That's because there are 2 nitrate ions per 1 cobalt 2 nitrate. So that's how they split apart. So we talked about this. You have electrical conductivity when you have a salt solution, not a sugar solution, because you're in the salt solution, you're having a physical breaking apart into ionic components, giving a plus and a minus charge. With that charge gives it an easier electrical conductivity. And these are called electrolytes. And then you have things like sugars that are non-electrolytes. So the definition of a strong electrolyte, even with splitting electrolytes and non-electrolytes, there is a further splitting, further branching off of different types of electrolytes. So those being strong and weak. So the strong electrolytes are these strongly soluble ionic salts and also strong acids considered to be in this category. Now, the definition is they dissociate completely into ions. So out of 100 molecules, NaCl is a perfect example, hydrochloric acid, great example. Out of 100 molecules, you're going to have 100 dissociations, and they're all going to break apart. This is what a strong electrolyte is. Then there are weak electrolytes, where out of 100 molecules, maybe 4 of them break apart, and 96 of them stay as their original molecule. They don't break apart. So you could wonder, okay, what kind of molecules do this? So not ionic usually. It's, well, not usually ionic salts, but it's usually weak acids and weak bases that do this. And here it says weak acids and solutions conduct electricity. Yeah, we know that. But they conduct electricity, and you can imagine since they're weak, they do it very weakly. And really weak acids and weak bases are that. So a question that you should have, and I'll give you the deets in a minute, is how the hell do you determine a weak acid and a weak base, and a strong acid and a strong base? So I want to know the difference, right? So we'll go over that in a slide or two. But basically, before we do that, we should cover the definitions of acids and bases. And we're going to cover this when you're going to go really in depth in Chem 2 about acids and bases. But generally, an acid has a hydrogen, and we learned about naming acids and bases, right? So you should have an idea of them already, where the acids, they have hydrogen in front of their name, or in front of their formula, usually. such as HCl, H2SO4, HNO3. They have an H in the front. That's usually the main way you can determine if it's an acid or not. And this acid tends to, this H tends to dissociate. So acids, they're by nature, they want to become proton donors, is what they call them. So an H plus, they want to form this H plus ion that's written here. This H plus ion, we call a proton. So we call a proton donor. And these acids like to be deprotonated, meaning the proton comes off when they're put into a solution. And whether it's a strong electrolyte, a strong acid, or a weak electrolyte, weak acid, it depends on the acid. That make sense? Any questions? Okay. So then you have bases. So bases, they dissociate in water, not to create hydrogen, not H+, but to create or to form OH- ions. So a lot of these bases are hydroxides that already have OH ions, such as magnesium hydroxide, calcium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, whatever. But some of them, there's one weak base that you should know, and I'll write it in the next slide when we go over the weak and strong, but it's right here. It's ammonia, NH3. So NH3 is a weak base, and you've probably all heard of ammonia, and you probably know what it smells like. Smells like piss, right? So, but ammonia is one of these weak bases. Now, it doesn't have a hydroxide by itself, but if you put it alone into water, it creates a hydroxide. It forms the hydroxide. And we'll look at the equation in a few slides for that. Okay, I'll have to write it then. Okay, so yeah, last thing on the slide is when you add an acid and a base together, it always creates a salt and a water. So this is an acid-base neutralization reaction. So what happens is, very similarly to what we're going to learn today about precipitation reactions, what's going to happen is the anions and cations will switch in the reaction and something new will be produced. And same thing here, where you add an acid and a base, let's say the cations, meaning the H and the Na, will switch. So you'll have NaCl, which is aqueous salt, and then you'll have HOH, which we know as water. And no matter what salt or no matter what type of acid and base you're adding, all the time it will create some kind of salt and definitely water if they react together. So yeah, that's how that works. So now I want to talk about this weak base stuff. So I guess we'll just, there we go. We'll go over everything right here. So strong and weak bases or acids. Okay, so this is something that's not in textbooks, or at least the acid part of it is not in textbooks, and me and my friends developed when we were in undergrad. So there is a saying, and this saying should be getting popular now because I've been teaching for 4 years, but no, it's not catching on. But it seems to help most of my students. Now, for the strong acids, there's a very easy way to memorize them. So I'm going to say this saying, then I'm going to write it down, and I'll say it again, and I'll write it down. I'm only going to write it down once, but so I'll say it. Hickle, hibber, high, hino, hicklo, hisso. Weird, right? Okay, so I'll say it slowly. Hickle, HCl. Okay, what's in the chat? Thank you, Adi. Oh, Dwayne, I didn't take attendance. I'll take attendance at the end. All right, so because I'm on a roll. Hickle, hibber, HBr. Hickle, hibber, high, hino, hicklo, hisso. So hickle, hibber is HBr, hydrobromic acid. High, hydroiodic acid. Hino, it's not perfect, HNO3, right? Hickle, hibber, high, hino. Okay, Kai, thank you. I saw that you heard it. If you heard it anywhere besides me, I would have been like, plagiarism, but it's from me. It's from my crash camp stuff. So hickle, hibber, high, hino, hicklo. There's actually 2 hicklos, so it's not perfect. Hicklo is HClO4 and HClO3, and HISO, which is H2SO4, which is the strongest one. And they're not in strong to weak order by any means, but this is a list of all of the very common, let's say, non-organic salts, the non-organic strong acids. So this is not all the strong acids by any means, but the ones that are beyond this list are beyond any undergraduate chemistry class. We'll put it that way. And beyond, and organic chemistry related that have super long names. So we'll put it that way. So yeah, so Hickel, Hibber, High, Hino, Hiclo, Hiso. And there's the two Hiclos. You have, what is that, perchloric acid, and then you have chloric acid. So yeah. Okay, cool. So now, and the good question you can ask is, oh, what about the weak acids? Is there an acronym for that? The answer is no. There's no acronym. But if you know the strong ones, by process of elimination, you know the weak ones. So anything that's not on this list, this Hickel, Hibber, High, Hino, Hiclo, So, is a weak acid. So I'll put everything, but it has to be an acid. I'll write everything else, but everything else that's an acid. And examples, HF, H3PO4, phosphoric acid. This is hydrofluoric acid. This is hydrosulfuric acid, H2S, not H2SO4. H2SO4 is sulfuric acid. And remember when you have the monatomic anion, it's hydro, you put the hydro in front, so hydrosulfuric acid. And then other ones, you have acetic acid, which is HC2H3O2, and etc. Really anything else that's not on the strong acid list is considered a weak acid. Okay, then you have strong bases. There's no cool saying for strong bases, unfortunately. And this is written in textbooks that it's the group 1A, 2A hydroxides, for the most part, the ones that are soluble. Some of them are not the most soluble, such as magnesium hydroxide and calcium hydroxide. They're kind of like very mildly soluble, but the ones that are considered to be strong bases. So group 1A, 2A hydroxides. Examples, you have NaOH and KOH are always the go-to strong bases in labs. Other ones, you have strontium hydroxide, and whatever, there's more, but group 1A, 2A. And then for weak bases, it's basically everything else. Get it? Basically. But it's basically everything else that's not on this list. And there's one such as the other hydroxides. Like if you have transition metal hydroxides, those are going to be weak. But there's one that you should know, and that's ammonia. So I'll write that down. So I write everything else hydroxide plus NH3, which is ammonia. There's also other ones, like in organic chemistry, a lot we use like calcium carbonate, magnesium carbonate. Those are really weak bases that are in like antacids. So like calcium carbonate is in a lot of antacids. It's pretty weak. Even though it doesn't have a hydroxide in it, it's still considered to be a weak acid, or weak base. Sorry. Okay, so yeah, NH3. So something important about NH3 is when you add it to water, it's the only one of these bases that we're going to cover that doesn't have hydroxide to directly give up to the solution. So I said before that it produces this hydroxide. And the question is how? So what you're going to do is you write an equation. NH3 plus H2O yields whatever it yields. Now, water has this cool property is that it can act as either an acid or a base. So those of you who took high school chemistry, you know that it has a pH of exactly 7. And it's neutral, completely neutral. And the reason why it's neutral is because out of the acid component and the base component, it has an equal part of each one. It's comprised of H, which is the acid part, and OH, which is the base part. So OH is characteristic of bases, H is characteristic of acids. Put those together, you get something completely neutral, which is water. Now, another thing about water is that it has this cool phenomenon in that it's amphioteric. So amphioteric, you don't even know that term, that just means it can act as either an acid or a base. And most things that are neutral and that have a place to accept hydrogen or to remove hydrogen from are considered to be amphiotaric. And water is a great example. So depending on what it's mixed with in a solution, it can either act as an acid or a base. And it usually acts as the opposite. So for example, in this case, we're adding NH3 to water. NH3 we know is a weak base. So H2O will be like, oh, I don't really care. I could either gain hydrogen or lose hydrogen. But since you're a base, you want to gain hydrogen. So something else about a base, it likes to lose OH or gain hydrogen. OHs and hydrogens are opposites in acids and bases. The acids want to lose them, the bases want to gain them. So the water's like, all right, I'll give up my hydrogen to you because you're a base and you want to do that. And the NH3 is like, sure, man, I'll do that. He becomes NH4+. That's the ammonium ion. And you know that one from one of the polyatomics. It's the only positive polyatomic cation that we went over. And also what's left over is after this water gives away that proton, you end up with O, it's a weird O, OH minus. And this is how ammonia as a weak base can produce a hydroxide ion in solution by using that amphiotaric nature of water to give that hydrogen from water to the ammonia that creates this hydroxide ion in the solution. So yeah, that's how that works. A lot of the other ones are pretty straightforward. Like NaOH would just dissociate into Na plus and OH minus. And then the water would just engulf each one of those, just like we know. But for ammonia, it's worth mentioning this specific process of the transfer of the hydrogen of water. But yeah, so any questions on those? Yeah, so it's something that you should be familiar with. It'll help you. I don't think the other classes aren't going to learn this about strong acids, only us because we're special, and it's not taught anywhere. So yeah. Okay, so other things about strong acids is they just like they're a type of strong electrolyte, so they go through 100% ionization or 100% dissociation. And here's an example: 100 molecules, you expect 100 ions. We talked about that. And the weak acids are different. They go through a lot less. So this is a little bit drastic. It varies, but it's usually around 1 to 3%. In this case, they said if you have 100,000 molecules, only one of those will dissociate. Maybe for some, but I mean, this is for HF. HF's not that weak, honestly. It's probably maybe one out of 1,000, but not one out of 100,000. But so I mean, the idea here is that the weaker the electrolyte, the less ionization it goes through, the less conductivity it's going to have. So it's important to know. But mainly, the most important thing to know is to be able to classify strong, weak, and non-electrolytes. So we went over strong, we went over weak. Now let's go over, we went over non already too. So yeah, non-electrolytes are going to be anything sugar. Even if it's not a sugar, or a good question to ask is, how do you know if it's a sugar or not? Now, sugars have, if you look at the three-dimensional structure, they have a ring. They're usually a ring with hydrogens, or with, carbons and oxygens. But if you don't know that, you can just say that it's a complex structure that you can't break apart into ions based on the ions you know. So based on everything you learned from chapter 3 and 4, you should know that you have your polyatomic ions, you have your cations, and you have your anions. In everything, in the weak electrolytes and the strong electrolytes, you can clearly pick out your ions. So even for this weak electrolyte here, this H+, oh, it's an H in front of it, probably an acid. And this C2H3O, what ion is that? Acetate. Acetate. Nacho. I like that. For sodium acetate, nacho. Cool. This is acetic acid, this HC2H3O2. Now that one, if you knew that polyatomic ion, you'd be able to split it apart into its components of acetate minus and H+. And then obviously for the strong acids, you have all soluble salts, so you can break those up pretty easily. But for the non-electrolyte, you can think about it all you want based on the knowledge that you're supposed to know, There's no way to break this apart into ions. So if you come to that conclusion when you're going through your mental processes to figure this out on a homework or an exam, you could think, all right, I can't go through any of that. I can't split it apart anyway. It's probably a non-electrolyte, and you'd be right. Okay. Any questions so far? I feel like I've just been yapping. No. Everybody online is quiet. Everybody probably fell asleep. Okay. Continuing. So now I did mention before that there are soluble ionic salts. This also means there are non-soluble or insoluble ionic salts, and this is true. So how do we determine which one's which? There is rules. These are called the solubility rules. There are many different charts that show the solubility rules. This is my favorite chart because it sums them up in the best way possible. That's easier to memorize. And yes, you do have to have them quote unquote memorized, but they're pretty easy to memorize because a lot of the rules kind of conflict with each other. Like if you know, for example, if you know the first 3 rules, you're probably good for like 90% of things based on process of elimination and the rules. So we'll cut to the chase. If you really have no idea, just guess that it's soluble because most ionic compounds are soluble. Also, if you have a reaction and you know that one of them is soluble in the product, chances are the other one's not going to be soluble because these reactions, in order for them to occur, you need to have a precipitate product, which we're going to learn about in these precipitation reactions, meaning that there has to be one insoluble solid component that is produced from the reaction. If there isn't, then no reaction will occur. In some cases, you might have that, where no reaction occurs, and they're just testing your knowledge. But it's important to know these solubility rules. So I'll go over all of them, really, and the trends and how to think about it. So all of the, not only limited to lithium, sodium, and potassium, and ammonium, all of the group 1A metals are soluble. So if you see lithium hydroxide, lithium whatever, it's soluble. Same thing with sodium, with potassium. Ammonium they throw in there too, even though it's not technically a group 1A, it still has the charge of a 1A because it's positive 1. And it follows those rules as well, that it's soluble, no matter what it is. Next, nitrate and acetate. So now it's important to know acetate because it's one of those ones that if you see it, whatever it is paired with, whatever cation it's paired with, automatically soluble. So same with nitrate. So if you ever see a nitrate, no matter what's in the front, automatic solubility. Same with acetate. Those 2 rules right there would get you'd probably be okay. If you were really intuitive and smart with your reasoning, you'd probably be good with those 2 rules. But it's important to know a couple more. Now, chlorines, bromines, and iodines, and really most other things are insoluble with silver, mercury, and lead. You can see that in rule 3, 4, they come up, and everything else insoluble with other ion, insoluble with other ion. So in the last 4 rules, silver, mercury, and lead are included in things that are not soluble. So this means that if you have any of those 3 ions in your equation, silver, mercury, or lead, that should raise a red flag to you. That should be like, whatever reaction this goes through, whatever silver, mercury, and lead is with, that's probably going to be insoluble. So I better watch that because in a lot of different things, they're insoluble. So just keep that in mind. That's another rule. And then with every other ion that's not them, the chlorines, the bromines, and the iodines are soluble, and the sulfates, basically. Strontium sulfate, barium sulfate are 2 exceptions. Yeah, but there are weird exceptions, like things like that, like strontium and barium sulfate, they're just not soluble. It kind of goes against, it's kind of just like a niche rule but hopefully other things in the equation. I mean, try your best to memorize it, but I'm saying in a student's perspective, don't focus on the little tiny rules too much. Just focus on the big ones I'm emphasizing. The lithium, sodium, potassium, ammonia, the nitrate and acetate's always soluble. And to raise a red flag with silver, lead, and mercury. Everything else, is good to know. It'll definitely help you and make it easier for you. But with deductive reasoning, you should be able to figure that out. And we'll do examples. Other rules, you have carbonate and phosphate. They're soluble with the main four, these main four that are written in the first rule, insoluble with everything else. So this is basically saying that carbonate and phosphate are always insoluble unless they are in the group 1A, these four. The lithium, sodium, potassium, and ammonia. So it's kind of conflicting with the first rule. I mean, so it's saying insoluble unless the first rule. So also you have hydroxide and sulfide, soluble with all of these, insoluble with everything else. So for hydroxide, it's basically telling you if it's not in group 1A or some of the 2A's, then it's insoluble, which this rule is technically not that true. Like iron hydroxide is, so solubility, I'll tell you right now, solubility isn't on and off. It's not binary. There's partially soluble, weakly soluble. They call it sparingly soluble. So things like a lot of the transition metal hydroxides, and even things like calcium hydroxide, but things like magnesium hydroxide, which is technically insoluble with any other ion here on the bottom, that's soluble. That's weakly soluble. So it depends what concentrations you're talking about. So they all have solubility ranges, but the ones that are considered to be soluble here are like very strongly soluble. So there is a range, but based on this knowledge, you'll still be able to figure out. I'm just telling you the technical information so that you understand how it works. It's not just soluble, insoluble. The way solubility works is there's a threshold. So if you could do this when you get home, if you have enough salt, you could just take a little cup of water, clear cup, and put some salt in. Mix it around until it dissolves, put more in, mix it around, more, until it doesn't dissolve anymore. At that point, you reach the solubility threshold. And for NaCl and water at room temperature, it's, I don't know, maybe a gram, maybe like 0.9 grams or something per milliliter. I don't know. It's something pretty high. Like water can take a lot of salt, a lot of NaCl. But for other ions, let's say one that conflicts with these rules, magnesium hydroxide, for example, the solubility limit might be 0.0 or 0.1 gram per milliliter. So if you put up to 0.1 grams, it's still going to be soluble, but not too much. It's going to be tenfold less than a strongly soluble compound. So there is that range. So we'll do some practice. So HCl, strong, weak, or non-electrolyte? These are homework questions. Good, strong, awesome. Strong electrolyte, Hickel, Hibber, high, Hickel, right? Acetic acid, strong, weak, or non-electrolyte? Weak, good. It's not Hickel, Hibber, high. It's not, no, it's it's Hickel, Hibber, high, no, close up. Yeah, Chico, Nacho. What conducts electricity in metals? One word. Random question, I know, but you can figure it out. Not ions. So in a metal, like you have a copper wire, what's going through it? Electrons. Good. Now, what conducts electricity in a solution? Electrolytes is closer. So what does ions? Yeah, the first you because the presence of the ions in the solution allows it to be an electrolyte. So that's how the electricity is moved. So whereas in one big piece of copper wire, the electrons are freely going through it. So that's what makes it conductive. So we went over this already. So strong acids, high, no so. Strong bases, 1A, 2A. Weak bases, everything else. Weak acids, everything else. Okay, so types of reactions. So now we're going to go over, we kind of already went over redox. So that'll be a review. But we went over redox, right? Yeah, okay, cool. With the oxidation states, yeah. So we'll go over precipitation reactions, which is a new one. And acid-base we've seen, but we'll just go over it again. Okay, so a precipitate. A precipitate is a solid that will form in a solution when two ionic salts are mixed together in an aqueous solution. Now, it will create this precipitate. So precipitate means a solid component of it. So what will happen is the ions, or let's say the cations, will switch of the two ionic components that are mixed. And then that product of those ions switching is an insoluble product based on our solubility rules. And that's called the precipitate. Kind of the opposite of precipitation, like rain, it's actually going to be solid instead of liquid. So here's an example where you have, and we'll write this equation now. We'll do this right now, this example. And there's different things you can do with these. Oh, I think they did it for us, but whatever, we'll do it anyway. Okay, so this reaction, potassium chromate is added to barium nitrate. So we have K2CrO4 plus BaNO3 2 is going to yield. So what happens with this reaction is the cations will switch, or the anions will switch, however you want to look at it. And you'll end up with KNO3 plus barium chromate. Now, the charge of chromate, what's that? You can tell by looking at potassium chromate. Good, -2. So it'll just be, and barium is what? Yeah, +2, because it's with two nitrates. So barium chromate. So it'll just be a 1-to-1 like that. Yeah, definitely review your charges, review your polyatomics. So I want you guys to be like, if I tell you barium, 2+, chromate's a tough one, but like something like nitrate, 1-. You got to be on it. Okay, so when these react, the cations will switch, and you have potassium nitrate and barium chromate. So let's do some balancing first. You have 2 Ks here, 2 Ks there, and then, okay, it's all good, balanced. Very quick one. Okay, so now, even though we just learned the rules, who can tell me, out of each one of these, out of, let's say we'll call them 1 and 2, which one is insoluble? Which one will be our precipitate? The second one, good. That's because the rules we went over, I stressed potassium, anytime you see potassium, soluble. Anytime you see nitrate, soluble. You put them both together, super, super soluble. So one will definitely be an aqueous, so it'll be in the aqueous solution. You won't see anything, meaning. So if you were to do this reaction, this yellow that you see, that would be the barium chromate. The potassium nitrate won't actually form. It won't be potassium nitrate. It'll just be free potassium ions and free nitrate ions. Meanwhile, the barium chromate will stick together because they will stick together and what we call fall out of solution, meaning they will no longer be part of the aqueous pluses and minuses. They will become a solid and fall out of the solution because of their lack of solubility. This is basically how a precipitation reaction works. So there are many things to do with a precipitation reaction. When you're given one, the question you're going to be asked is to find the net ionic equation. So net ionic equation. Now we'll go over what that means with a example. We went over this one already. Oh, they use barium. Oh, they use the. Okay, fine. So we already have. Okay, so we'll just talk about this one. We already did it. So we have the same reaction here. We have the potassium chromate and the barium nitrate make the potassium nitrate and the barium chromate. We know the barium chromate is a solid. So S doesn't stand for soluble, it stands for solid. The AQ means it's soluble, meaning it's aqueous. So we should put an AQ next to these two as well. Okay. So what does this mean? Now, the next step we do is after we have the overall formula is we can create something called the complete ionic equation. And I'll just copy that away from now. We'll call this the overall formula equation, and then we'll have the complete ionic equation. So a complete ionic equation is actually very helpful. Complete ionic equation. It tells you the representation, or the accurate representation and behavior of each of these ions in an aqueous solution. So whereas the overall formula equation doesn't. So the complete ionic equation, once we split it apart, will tell you if I look into this water and take a scoop of this water, what will I see? And you won't see potassium chromate, I'll tell you that. What you will see is you'll see for every 2 potassium ions that are separated, you'll see a chromate anion. So what I'm doing is I'm splitting apart the ionic components that are aqueous. Because if you look at this reaction happening in water, these potassium ions and the chromate ions will never actually, or they won't actually stick together. Because what did we talk about dissolving? You put a potassium chromate or an NaCl crystal into the water, what happens? The water molecules attack them and split them apart. That's what's going to happen here. So if you look at them, if you look at a sample of the water at any random time, you're going to have potassium ions that are by themselves and chromate ions that are by themselves because they're both soluble. Now, the reason why you have 2 potassium is because you can't have K2. So the reason why it's K2 and then chromate is because there's 2 potassiums bonded to that chromate. Once they all dissociate from one another, you can't have K2. It'll just be 2K plus, like that. Any questions on that, how I did that? All right. Then we can continue. And we know that barium nitrate is also soluble. So we would put barium 2 plus AQ. And the notation here is important. You know, it's kind of technical. You have to write the charge, the amount of them as a coefficient, and then the AQ. And then you have 2 nitrates, 2 NO3 minus AQ yields. Now, since potassium nitrate is still soluble, you have 2K plus AQ plus 2 NO3 minus AQ plus the solid. Now, the solid does not break apart because if you take a sample of this solution, the barium chromate will be barium chromate because it came out of the solution. It did not dissolve. There is no longer the ability to dissolve. So you'll have BaCrO4 solid. And that is your complete ionic equation. So it's an accurate representation of, on the molecular level, what ions do we see, which ones are bonded together, which ones are not. And basically, the way this works with all precipitation reactions, you're going to have 4 free aqueous ions. In this case, you have potassium, chromate, barium, and nitrate. Some combination, or really one combination of those cations and anions will create an insoluble component. That insoluble component is the precipitate. That is how the reaction occurs. If all of your components and all of their combinations are soluble, then no reaction will occur because there's no way anything will change. Those free ions will just keep spinning around and they won't actually bond to anything and become precipitate. So yeah, that's how this happens. Any questions on that? And there is still one more thing to do with this equation. Yes. Okay, so the point of writing it like this, good question, is we want to write, at the end of the day, what we're going to do next is we're going to write the net ionic equation, which is the one on the bottom here. So it tells you out of the entire complete ionic equation, or the entire formula equation, which two ions are contributing to the solid. And everything else is excluded because everything else is considered what we call a spectator ion. That's just going to be in the solution. But you can kind of think to yourselves, like, we're pretty smart. You can be like, all right, why can't I just write that in the first place, right? You could, but the idea here is more, it's more conceptual. So if you looked at the formula equation, you would see, all right, I have potassium chromate and barium nitrate, and I'm mixing them. That's not what's happening. You're having a solution, aqueous solution of potassium plus and chromate 2 minus and barium 2 plus and nitrate minus. That's being mixed together. And by molecular motion, eventually the correct ions will meet that form the solid, the barium and the chromate. Then they come out of solution. So it's a much better representation of what actually happens. But if you want to cut to the chase with it, you totally could, because you're smart. So, good question. Okay, so next is just the rewritten complete ionic equation. And now what we need to do at the end of the day is to create the net ionic equation. And this is just using algebra skills. So what you would do is you would cross out what's common on the left and right. So on the left and right, you have 2K plus. On the right, you have 2K plus. That goes away. You have chromate. Oh, you don't have chromate by itself here. That stays. Same with barium. You have barium 2 plus, barium chromate. And then you have the 2 NO3 minus. That would cancel. The things that we just canceled are called the spectator ions. Perfect. That was a perfect cut and paste. So the ions remaining in solution, the K plus and the NO3 minus, are called spectator ions, meaning they don't actually participate in the reaction to create the product. They're just in the solution to begin with. So we call them spectator ions. Yes, the ones that crossed off with the spectators. The ones that are left over are not the spectators. They're the ones that directly participate in the creation of the precipitate, of the solid precipitate. So for those, you'd have the chromate, the barium, and the barium chromate, and that would lead us into our net ionic equation where we just write those, and you'd have Ba2 plus CrO4 2 minus yields barium chromate. Cool. So any questions on that? Continue. Now here's another list of the solubility rules. Basically the same rules. Yeah, really the same 5, 6 rules, but it's just the chart from the book. There's another way of thinking about, or the same way of thinking about it, just illustrated. You have potassium nitrate, or what do you have here? You have lead nitrate originally, and then you have potassium iodide. So you mix those together, and you're going to get 2 possible products. You'll get KMNO3 or KNO3 and lead iodide. So out of these, which one is soluble? Which one's insoluble? 2, yes, the lead iodide, right? It's one of those red flag ions, the lead, and then you know that anything with a nitrate or anything with a potassium is considered soluble. So you'd have questions like that where it's kind of clear cut. And if you look at the rules, I would say for 20 minutes and then do the homework, you should be comfortable enough to figure out which one's soluble and which one's insoluble. So lead, mercury, and silver are like the red flags. Okay, So here's a question from the homework. So in the reaction AgNO3 plus NaCl, both of those are soluble, of course. Which one is the precipitate? 1 or 2? 2, good. And that 2 is AgCl, right? Because, because you have silver, so silver chloride. And also you know that, even if you didn't know that, you know that, oh, NaNO3, you know that's soluble, but that's nitrate. And something that's important is it's not the ions. The ions are never the precipitate. It's always the solid that forms from the whatever combination of cation and anion. So it's either A or B. I mean, it's definitely not the other ones, but we know it's B because of the rules. Okay, cool. All right, so stoichiometry. You can do stoichiometry too. With basically, everything we learned last chapter still applies to these balance equations. It's the same thing. Okay, so acid, base, and redox. This is kind of a review. What are we learn about? We kind of saw this already, but so anyway, no point in going over it again. But I mean, acids and base. Any questions about acids and bases so far, or anything else you want me to cover about it? We talked about the acid and a base yields a salt and water, and that salt could vary. So there's the textbook list of acids and bases that are weak, or sorry, strong. I like Hickel, Hibber, High better. They do Hickel, Hibber, High, Hino, Hiso, Hiclo. Ooh. But and they forget HClO3. That's also a strong acid. They forgot about that one. And then everything else is weak. So yeah. Okay, cool. So another thing that's kind of important is this thing called an acid-base titration. Now, what that means, what a titration is, it's a very common laboratory experiment. There's different types of titrations. An acid-base titration is one of the most basic ones. And what a titration is it is a technique to determine the concentration of an unknown solution by adding a known solution, meaning you know the concentration of it and you know the identity of it. So the way this works with acids and bases is, let's say most of the time you have an unknown thing of acid. You have, let's say, a known volume. You know what type of acid it is, but you don't know the concentration. There may be cases like this. It's a very easy, like in lab with, if you want to know, if you create an acid, let's say, and you don't know the concentration of it, you can take some of it, do a titration of it, and see how much is in there, and how much concentration. So the way you're going to do this is you're going to keep adding base at a very fine amount, like drop by drop, until the acid is neutralized completely. And that by that point's called the equivalence point. You'll know, since I added X amount of my known base, using the equation and using stoichiometry, I can figure out how much of the acid is in there, how many moles. And since I know the moles and I know the liters, I can divide those two and figure out the molarity and figure out the concentration. So how do we know it's neutralized? That's the next question. So if you just add, these are all clear liquids in chemistry, right? So if you just add a clear liquid to another one, chances are it's not going to do anything. With acids and bases, if you add an acid to a base or a base to an acid, you'll get some fizzing. It'll fizz a little bit. But that's about it. You don't really know for sure until you add this thing called an indicator. So an indicator is a dye that is environmentally sensitive. And by that we mean chemically sensitive and chemical environment sensitivity. So there are different types of indicators, and one of the most common is phenolphthalein. Phenolphthalein, it's like pH, I don't even know how to spell it, but it's the most common one. And what it does is you add a couple of drops to the acid, and once the pH is very, very close to 7, which is the neutral point, it will turn pink. And when it turns pink and the solution stays a pink color, that means the solution is neutralized. So you're going to keep adding drop by drop this base until you have this pink color. That's where the equivalence point is, meaning that is where you stop the addition of the base and you know this amount is the amount of base that's required to neutralize my unknown concentration of acid. And based on that number, I can figure out the moles of it, or the moles of the base added, meaning if it's a 1-to-1 ratio of the moles of base added to the moles of acid neutralized, which some cases it is, I can figure out the amount of acid in there. So here's an example. The most common acid-base titration is NaOH plus HCl. If you add those together, you get H2O plus NaCl, a water and a salt. Now, if you add, let's say you have, did we go over molarity in this class? I don't think we did, right? No, molarity? No, we didn't. Okay. So anyway, molarity, I don't know why they talked about it, but we can go over it. But molarity is the easiest way, the SI unit for concentration. So what you do is the moles divided by the liters. Very easy. So what you can do is, let's say you have 250 milliliters of HCl, an unknown concentration of HCl. To neutralize this HCl, it takes you 100 milliliters of the NaOH that is 0.5 molar concentration to neutralize it completely. The question would be, what is the concentration? So what is the concentration? What is concentration of HCl? So that's what the question will ask. If it's unknown, you have 250 milliliters of it, you neutralize it with 100 milliliters of 0.5 molar NaOH. So here's how you would solve that problem. But first, does everybody understand or have any questions about what the problem is asking for? No? Okay. So you have the equation. The equation is going to help us. And it's balanced too. So any ideas on what we can do first? And it has to do with this equation, the molarity equation. And big M is molarity. Yeah. Yeah, so kind of. So you can use it, but let's see. Calculate mole. So how good, that's a better answer, but you're on the right track. So to calculate the moles, you can calculate the moles of NaOH. Is that what you're getting at? Oh yeah, okay. So you calculate the moles of NaOH by using the molarity of 0.5 molar equals X amount of moles divided by 100 milliliters, or 0.1 liters. Multiply that over, you get 0.05 moles of NaOH. So that means to neutralize this unknown amount of HCl, you added 0.05 moles of NaOH. Now, let's look at the equation. This equation tells us to neutralize HCl, you need, or to neutralize 1 mole of HCl, you need 1 mole of NaOH. All right, I neutralized HCl. I needed 0.05 moles of NaOH. That means that there must be 0.05 moles of HCl in there. And you'd be right. So now, with that amount of moles of HCl, what do we do? What can we do? If we're being asked for the concentration or the molarity of the HCl, what would be the next step? Perfect. Yeah, good. So you divide by the volume. So you can take that moles and use the same molarity equation we used before. But this time we will solve for molarity. So for the HCl, it would be 0.05 moles divided by 0.25 liters. And that would be the concentration of the HCl, which would be 2, right? 0.2. Yeah, that. You got it. 0.2 molar. So you would know that you'd have a 0.2 molar or 200 micromolar or 200 millimolar, whatever you want to call you'd have that amount of HCl. So that is acid-base titration in a nutshell, using equations of molarity. So molarity is another important equation that it's not technically covered in this chapter, but we're going to see it. So, and it's very important for chemistry. So moles divided by liters, and tells you the concentration of really anything you have, if you know the moles and liters. So very important. Okay, any questions on that? No? Okay. All right, so oxidation reduction, we're almost done basically with chapter 5. We'll start talking about chapter 6. It's only 7:44. I guess we'll start chapter 6. We'll start like a good chunk of it. So oxidation reduction, just to review. So oxidation, you have this oxidation number, right, in the equation. The oxidation number increases if you are oxidizing. This means multiple things. This could either mean the element loses electrons. Well, it definitely means that. Definitely means it loses electrons. It could, but not all the time, means it adds oxygen. So if you are adding oxygen to something, you're oxidizing it. If you're losing hydrogen, because oxygens and hydrogens are antagonistic, if you're losing hydrogens, that could be oxidation as well. Doesn't have to be. So you don't need to look for, like we saw last class, it's not more complicated than what we saw last class, when we're just determining the numbers between the left and the right side and figuring out which one's oxidizing, which one's reducing, which one's the agent, right? It's not much more complicated than that. So other things to look for is in oxidation, if you're adding oxygens, if you're losing hydrogens. Don't worry about half reactions yet. And then reduction is the opposite of oxidation. So and they both have to happen inside one equation. So for reduction, it's the decrease in the oxidation number, which means the increase in electrons, the loss of oxygen, or the gaining of hydrogen. So you see a lot of these will happen at the same time, but not all of them need to happen. If you have an equation without oxygen in it at all, it could still be redox, totally. But it doesn't have to be. Yeah, okay. Cool, so here's the rules again for the oxidation states. We'll do some example. We'll do another example. Oh no. Go away. Oh no. I want you to see the answer. Okay, no more answer. Nope. Close your eyes. Too late now. But... Okay, so we'll do this one together. So let's bring back those rules. So first things first is to find the oxidation state of all of the different elements. So hydrogen, we know is +1. So write +1. Sulfur would then be what? Good, -2. Now oxygen is what? -2. Good. Now this NO3 has a minus charge totally. So what would this nitrogen then be? Good, +5. Because +5 minus 6 from the oxygens equals -1. The hydrogen, so here's another rule that I didn't specifically go over, is that even if something is in its elemental form, if it's an elemental form but an ion, such as H+, the oxidation number is +1. So that rule for the element being alone always applies unless there's a charge that overrides it. So, and this is H+, therefore the oxidation number would be +1. But if you look at 3s on the right side, this is elemental form, but there's no charge, therefore it's 0. Then we have NO, which oxygen's -2. What would this nitrogen be? Good, +2. And then we have two things we know and love, H and O. Cool. Okay, so now after you assign oxidation numbers to everything, your job is to compare the left to the right side, which ones are changing. So who can tell me which one is changing? One of them. one of the elements? Nitrogen, good. So nitrogen is going from +5 to +2. So is that being oxidized or reduced? Reduced, good. Reduced. And if it's reduced, it's the what agent? If you remember. Oxidize, good, it's the opposite. So oxidizing agent. So that means it's forcing the oxidation, forcing the oxidation of the other one. So we can look at the definitions of oxidation, or sorry, of reduction, and see them in action here. So NO3 minus, it becomes NO. It loses oxygens. That's another key for reduction, of losing electrons. It doesn't gain hydrogens, but it loses electrons and the number decreases. So that's usually indicative of oxidation, or sorry, of reduction. And then the other one, which is the other element that is changed? Good, sulfur. So sulfur goes from -2 to +0. Goes from -2 to 0. And this is being oxidized, meaning the number is going up. Also, oxidizing means you're gaining oxygen, which the sulfur is not gaining any oxygens, but also means reducing or decreasing the amount, or sorry, losing hydrogen. In this case, it's losing hydrogen. So you see how it has 2 hydrogens here, and here it has 0. So that's another way of thinking about redox by that definition. So also, since it's oxidized, is the what agent? Good, reducing agent. Good. All right, cool. And then that would be basically it on what you need to figure out in these kind of questions. So, yeah, got the hang of that. Any questions on that? No. Okay. Okay, solutions. Oh, dilution. Oh, there's molarity. Hey, there we go. Important. Good. So, last part, we're gonna talk about solutions real quick. So you can have dilutions. We're talking about dilutions also. The formula. Yep, we do. Good. So we can have a dilute solution or a concentrated solution. And the way you determine this is based on their concentration in molarity, which we talked about already. So molarity is the amount of moles of your solute divided by your liters of solvent, or liters of solution, sorry. So it's M equals MOLE, moles over liters. You could have a dilute solution, which is very dispersed solute particles in the solvent, or you could have a concentrated, which is a large amount of solute particles per amount of solvent. So an example I like to give for this, the under 21 example is, so like if I have orange juice, sometimes I like to dilute it. That's weird, right? But I dilute my orange juice sometimes. It's too sweet. Maybe I'm getting old. But basically, if I dilute my orange juice, oh, we have a comment already. You're gonna make fun of me. I do that. Okay, Victoria's on board. She does that. So if you make fun of me, you make fun of her. So don't make fun of me. But if you have a dilute solution, let's say you have orange juice particles, right? Let's say you put half a cup of orange juice, and then you fill the rest of the cup up with water. It's not like you can consider it as you're getting double the orange juice, but you're not. You're getting the same amount of orange juice particles, but they're more dispersed in the solution. So they're less concentrated, they're more dilute. And there's equations to actually dictate this. It's called the dilution equation, which we'll talk about in a couple of slides. And that's basically how that works. So the amount of solute stays the same, but the solution volume increases in a dilution. They have an indirect or inverse proportionality of concentration to volume. So the concentration goes down if I dilute something at the same time as the volume goes up. So a over 21 example is if you have hard alcohol, you tend to put like rum and Coke or something. You tend to put a chaser or some other drink in there to make it more dilute so you don't taste all the alcohol at once. But you guys would know about that, right? Because you're less than 21 years old. Of course not. But yeah. So yeah. And there's molarity, there's the equation. Yep, we saw that already. Okay. Let's do examples. Okay, so how many moles of H plus are in 216 milliliters of 0.49 molar nitric acid? So anybody want to tell me what to do? Yeah. Yeah. Good. Good. And Adi, good job. Everybody, good job. You're going to say the same thing, of course, right? So good job. Oh, more people saying things. Great job. Good job, Hal. Awesome. So you do the molarity equation. 0.49 molar equals X amount of moles divided by 0.216 liters. Now keep in mind, what is it asking? It's asking for how many moles of H plus, not HNO3. In this case, we're lucky that H plus is in a 1-to-1 ratio with HNO3. Not always going to be the case. So if we multiply these together to figure out the moles, we get 0.49 times 0.216, and we get 0.106 moles of H plus. Now, if this question was asking for how many moles of oxygen are in the same solution, what would you do? Yeah, exactly. So it would be 3 times your answer, because you know that in 1 molecule of HNO3, there's 3 oxygen atoms. So your number of moles of HNO3, you have to multiply it by 3 to get the number of moles of oxygen. 0.316 moles of O. Okay, cool. Now we'll do one more. So what is the molarity of nitrate ions when 0.56 moles of barium nitrate is dissolved in enough water to make 4 liters of solution? So what is the molarity of nitrate ions? That's important. So we can do the same thing. I'll do this one together. So molarity equals the moles, which is 0.56 divided by 4 liters of the solution. And we get a number, 0.56 divided by 4 equals 0.14 molar. Okay. So now 0.14 molar, this is the amount of barium nitrate. It's asking for what is the molarity of the nitrate alone. Each barium nitrate has how many nitrates? How many nitrates? Not oxygens, nitrates. Yeah, 2. So you're taking this number, multiplying it by 2 equals 0.28 molar. Cool. We basically did all the homework together. All right. So now I decided what we're going to do. So after we're done with this, I'm going to talk to you for like 2 minutes, since we're really early. I'm going to talk to you like 10 minutes about chapter 6. And then instead of leaving, we're going to start chapter 5 homework together. Right? Not together, but you could all start it, and I'll be here to ask questions. And we could stop if you have a question on one of them. So, yeah. Okay. So last thing is dilution formula. So here's the equation, and then I'll explain it. So you have M1V1 equals M2V2. Now what this means is that the concentration of your first solution, M1, has a certain volume, V1. If you want to dilute that solution to a lower concentration, that lower concentration would be M2. The volume required to do that will be calculated as V2. So any one of those 4 variables could be missing, and you can solve equations to figure it out, the 4th variable. So when you're doing this dilution, it doesn't matter which one is 1 or 2, either M1 or V1 or M2 or V2, as long as the solution is together, meaning the concentration is there for the correct volume. So we'll do an example. We'll do one example. M1V1 equals M2V2. Calculate the molarity of calcium hydroxide. Oh, that's another molarity one. Whoops. Next one. Nope, that's another one. What's this? Nope, that's too long. I want to read it. All right. So we'll come up with one. Doesn't it just mean that mass one? So it's molarity 1 and molarity 2. And no, they won't equal the same. So what this is an inverse proportionality equation. So it's a good thing that you mentioned that, Hal. So I can explain it. This means that, let's say you have concentrated solution, which we call the stock solution. So M1 is high, very high concentration, but you don't have a lot of it. You have a low volume of it. So you have high concentration of a low volume, and you want to dilute that. Let's say as a TA, right? I was a TA. What I do is I have a stock solution of hydrochloric acid that is 20 molar. So that is so high in concentration that it would like burn through your glove, and like it would really irritate your skin. It'd be terrible, right? But obviously for general Chem 1 students, we don't want them to be using that in the lab, right? We don't trust you, but and also the reactions don't require that. What we want to do is we want to dilute that 20 molar solution, which is a high concentration, low volume, to a low concentration, high volume for the whole class to use. And we dilute it to, let's say, a 0.1 molar solution. And we make a liter of it, or a huge volume that the whole class could use it. So that is how they're inversely proportional, meaning the concentration and the volume. The stock solution has a high concentration and a low volume, whereas the final solution has a low concentration but a high volume. So that's why we do these dilutions. Now, another question that someone in my other class asked is it possible to concentrate something rather than dilute something? And the answer is yes. You could easily, there's multiple ways of doing that. So, you know, dilution, you're adding solvent, right? But there's a way to take away solvent. So there's two ways. There's one way that we use in organic chemistry, and there's another way to do it in biology or biochemistry. So in chemistry, in organic chemistry, we can use this thing called, well, you can use distillation, or you can use this machine called the rotovate. And this machine uses pressure and heat to basically boil off the solvent. So let's say you have something, salt and water mixed in there, and you want to concentrate that salt a bit. So you will boil the water out, and then what's left over is the salt. And you can boil out as much as you want or as little as you want, and only the solvent will come out. That's one way of concentrating. Then in biology, there's another way of doing it. So I use this in my research all the time. There's these little things called concentration or concentrators, right? Very, very original name, I know. So it's a concentrator. And what it is it's this vial that has two chambers in it. The top chamber, I'll draw it. So the top chamber is kind of like this, and it has two membranes. So we'll put, it's kind of this like porous membrane. The bottom chamber is just a vial. So what you do is the cap. The cap closes like that. So what happens is you put your solution, or your, let's say it's usually what we're trying to concentrate is proteins or cells or something that's macromolecules, pretty big molecules that are thousands of grams per mole. Their molar mass is in the thousands. So what we want to do is we want to use this concentrator that has a cutoff. Let's say it's a 10K cutoff, meaning everything that's less than 1,000 grams or 10,000 grams per mole will go through that concentrator, meaning it'll go through those porous holes. Everything that's above 10,000 grams per mole, such as your proteins, your cells, or anything else you want to keep, will stay in here. Stay in here. So you put your solution in, and then close the cap. And in order to get your liquid or your solvent that is less than 10,000 grams per mole into the bottom chamber, is you put it in a centrifuge. And you spin that thing like hell. You spin it at 10,000 RPM, which is what? That's like 14,000 G or something. You spin it really fast. And what's going to happen is you could actually set the time, and on this on the pamphlet the kit that it comes with, it tells you how much time corresponds to how much volume. So if you had 200 microliters in here, you can spin it for 10 minutes and it'll decrease the volume by half. So you can kind of calculate what your new concentration will be after you concentrate it, and all the solvent that you don't want goes into here. So those are just two cool ways that scientists have developed to actually concentrate solutions. It's really cool. And yeah, sometimes, I mean, I honestly hate this method, because what happens is, with my luck and a lot of proteins, what happens is, in cell material, it sticks to the membranes. Sometimes it gets stuck inside, and then you can't recover it. There's no way of getting it out. So you're screwed. But that's a way to do it. Anyway, we'll do an example with M1V1. So let's say you have, we'll do the example I said for, let's say, a Gen Chem lab. Let's say you have a 20 molar HCl solution, and you have 20 milliliters of it. How much do you need? So how much volume? How much volume do you need? How much need? How much V to have a final concentration of 0.1 molar. So if you want to dilute 20 milliliters of 10 molar HCl, how much volume will you have if you want to aim for a 0.1 molar concentration? It's like, how much of your final diluted volume will you have? So what you can do is you simply plug in everything. So you're going to plug in your 20 molar times, you're going to leave it as milliliters. So something that's important with these kind of equations, and we'll talk about a lot next class when it comes to the gas laws, is, or actually no, we're learning about kinetic. I think we're learning about gas laws, yeah. So with the gas laws is that it doesn't matter what unit they're in for most of the equations, as long as it's the same on the left and the right side. And that goes doubly true for these inverse proportionality or direct proportionality equations. So it doesn't matter. So we can put milliliters here, and we know that our answer for V2 will have to be in milliliters also. The 0.1 molar times V2. So we're going to divide by 0.1, divide this by 0.1, and we get a number. So 20 times 20 divided by 0.1, we get 4,000. So we get 4,000 milliliters, or 4 liters. So that's how much we would end up with if we diluted 20 mils. Okay, cool. Any questions on that?